Thank you to the organizers for allowing me to present my research today. I'm always excited to describe what we do and what we've done with others. So I direct the Mechanics of Materials Research Group inside the Department of Mechanical and Aerospace Engineering. And if any of you want to talk more about making use of some of the resources that I'll be presenting here today, then simply send me an email. My email is very easy, ali@ucf.edu. And for any prospective graduate students who might be interested in some of the things that we do here, then you can certainly send me an email too as well. So with that, let's continue on here. Let's see. Okay. So my profile is this. I joined UCF's department, then the Department of Mechanical Materials and Aerospace Engineering back in 2006. And my research has largely been vectored towards solving problems related to structural integrity of materials or structures really facing high temperature and mechanical loading such as fatigue, so cyclic loading. The applications of that really are involving aerospace engineering, turbo machinery, some nuclear applications, pressure vessels and piping, and perhaps maybe some others as well. I'm active in ASME, and the two divisions that I spend the most time with are with turbo machinery and also pressure vessel and piping. Fortunately, I've had a lot of great students in my group. Some have moved on to academic positions, and the courses that I teach really revolve around mechanics of materials, and so for my fatigue course that I teach, I'm actually teaching it this semester. I've come to the point where I'm using my own written material, my own notes more rather than using books that other people are writing. So I really hope to have my own book soon. As far as other experiences, I've spent some time at Wright-Patterson Air Force Base working on hypersonic vehicles, and it's that work that led to a jointly funded NSF DoD REU site here called Hyper that I run with Dr. Jeff Kaufman and some of the faculty in Cater. So I also have a nice program where we talk about aerospace engineering manufacturing with our partners and our aircraft manufacturers here in Florida and also Brazil. I take students down there to see how planes are built as well. So, okay, so high temperature causes all sorts of problems, but the reality is that's the nature of how some structures are going to operate. They're either imparted to high temperature or either by design or just by usage, and it's really the hottest parts of a machine or a component or a device that really dictate the life of that structure. In some cases, the temperature either causes the mechanical loading or it's also applied, as a part of that. So in these things that I'm showing here that are over to the right here, you can see there was a breakdown in either design or the usage or maybe even the inspection of these parts. So electrical, structural, there's a variety of ways that thermomechanical fatigue or high temperature fatigue manifests itself. And so there's some structures, even like the blade that's right over here over my shoulder, we know what the material is, and we're trying to increase the service life. So people, coming to me saying, hey, we want to increase the life of this high temperature component. We want to double it. How do we do that? In other cases, where the materials are not so well defined, or the service conditions are not really well defined, such as hypersonic planes, we just don't know what the operating environment will be like. We know that there's going to be high temperature. We know that there's on the fuselage of the structure. We know that there's going to be sustained loading. We don't know how long the flights will be. We don't know, what the vibratory loads are going to be. So there are lots of question marks for that. So how do you solve those types of challenges without really knowing all the things that are necessary in order to do life prediction and fatigue analysis. That's really the crux of my work, is trying to figure out, well, how do we design, how do we figure out how long this particular material is going to last if we don't really know the service condition yet? Are there bits of information that we can use, to make first order approximations of that, and then go from there? So kind of inverting the matrix a little bit. So our group really works with highly engineered superalloys, nickel-based superalloys, and other metals. Some are anisotropic, like the DS material, the long grains that you see, or some are single grain materials, but many are dual phase, multi-phase materials that evolve with use. And if it evolves with use, then that means that that the behavior is going to evolve. The stress strain response, the strength of the material is going to evolve with use, which makes it very complex. So we're always trying to model the stress strain response, the deformation response of the material. So you're looking at our constitutive modeling that kind of goes through, test data for the material. And once we have a good mathematical model of how those things behave, then we can take it back to our partners and say, okay, well, try it on this component, see what it looks like. And then we're also developing life prediction models that predict, how long it's going to take for a fatigue crack to initiate in it. Of course, if it's running at one temperature, then it's going to have a certain life. But then when you start to prolong the temperature or its exposure to temperature, well, that has a factor. If you start to cycle the temperature, that all has a factor, and it can really play with the different mechanisms that cause the thing to fail. So it can be very unwieldy, especially when you can have all these things operating, a variety of different mechanisms leading to failure in a single component. And then, of course, that this also helps with the design and inspection part of it. Here you can see a transition piece that is subjected to high temperature, that has really bent down based on the high temperature and the pressure that's been it has been subjected to. Okay, so some of the constitutive, there are a variety of ways to model the cyclic plasticity of materials. There are some that are very, very basic models, like the one I'm showing you in yellow. These things tend to be built in your generic FEA codes, and then there are codes, there are equations that are ones like the red that I'm showing here, where maybe they're not built into code, but they have we're able to capture some elements of the evolution of the material here, some of the hardening and softening responses that the material kind of behaves like. And then there are other more complex constitutive models that capture the dislocation behavior that a material is going to see, in its microstructure. And this crystal viscoplasticity, is one of the most complex and computationally expensive ways to model a material. But it's also very accurate, because it can tell us, it can help us to model what the plasticity is going to look like, what the stress range will be, what the level of mean stress is going to be over time. And so we use those kinds of models in order to predict, things like hysteresis loops, like you see here. This one was a multi-axial one, so we were dealing with a chrome material. But I guess it suffices to say that if you give us the data, we can go and we can go and mathematically model it, based on the routines that we developed and based on just a little bit of information. We're also doing things like modeling combined cycle fatigue, and that is, that's even more complex, where you have the where you have the temperature cycling, mechanical cycling, and you also have vibration there, so we can model those things. One of our more recent breakthroughs really deals with dealing with these directionally solidified materials. Normally, someone would go and model individual grains, or make assumptions about grains that are in an element or in a structure, and you have to kind of go and model these things explicitly, and it takes lots of computational resources in order to do that. But we figured out a way to be able to still capture the anisotropy, but also reduce, make the computational, make the calculations a lot more efficient. So it runs 100 times faster. So whereas before, you only model critical locations. We can model entire components using very, very complex constitutive models. So that's the area that we play in. So it can be more informative when it comes to the life prediction part. So when it comes to the life prediction part, we need the constitutive model in order to do that, because we have our stress and the strains that we calculate. They go into predicting what the life would be. But we also, at the point of conducting experiments, we're also looking into the specimens to see what are the damage mechanisms associated with failure. So if you change things like where the maximum temperature is operating compared to the largest mechanical load, then you can really develop more of a map of what the mechanisms might be if given a certain combination of service conditions. So now we're not only able to take and predict what the life is going to be, what the stress strain response is going to be in a critical component, but we also can say what the damage will look like in that component. And keep in mind that in a component like a turbine blade, you can have several different competing mechanisms of failure that are happening at the same time. So here are some plots here that show our life prediction stuff. This actually comes from one of my thesis students. He had a best thesis of the year at UCF a couple of years back. This is a Goodman diagram that is showing the stress amplitude versus mean stress at different levels of life. So our models can go out to 10 to the 8th cycles, and it's very accurate. This is included in a paper for the International Journal of Fatigue. It's basically saying that at one set of conditions, creep takes over. At another set of conditions, it's more traditional mechanisms that take over. So these are the things that we tend to do. Going off into another vein of our research, we look at, we also, in the pressure vessel and piping community, we use statistics and also mechanics to optimize some of the processes that are used to, mate bolted connections. So here you see a couple of technicians that are up on the old STS, and they're connecting the ground umbilical carrier plate, which is used to transfer fuel over to the shuttle. And basically, these guys would go and develop the flange. There's a gasket that sits there that helps to make a tight seal. They would go tighten it, and then they would come back the next day and tighten it again, which is a costly process because it means that you got to wait a day in order to launch this thing. So now, based on some of our work, we're able to show, well, you don't need to wait a day. Just have them go up there just before lunch, wait a little while, come back after lunch, do the tightening without having to go all the way out to the launch pad. So that's, so we use statistics and mechanics to do that. It's based on experiments. We use finite element modeling, constitutive modeling to verify some of the results we get. And that work is, the natural progression of that is that as gaskets have become more complex, such as the textured gaskets that you see here, so now they're making gaskets that have little textures on them. We've been asked to characterize and optimize the designs of those things. I think it might not play. Regardless, these are areas where it's high temperature, high mechanical loads, and along the same lines of the work that we do with the superalloys and the metals, we're trying to predict the performance of these things so we can be able to tell engineers and scientists, well, how long will it take for a leak before a leak happens? And so that's going on in our lab right now too. So it's just showing, we have a textured gasket, and it's that texture that helps to create a nice seal across the width of the gasket. So that's some of the stuff we do, and we design, well, how big the hexagons can be and how high they need to be in order to do what they need to do at certain temperatures. Okay, our work has also gone into additive manufacturing, and so some of our partners have said, well, look, we want to do more. We want to have more components that that are made using additively manufactured processes. But the costs of being able to characterize these materials and optimize the processing conditions, it's cost prohibitive. What's a way to get around that? So what we've done is we've developed miniature testing, so puncture testing, in order to characterize what the strength and ductility of these materials would be. So what you're seeing here is hey, we conduct experiments on coin-sized samples instead of these larger samples, and we can cycle this. Right? We can cycle it to determine the fatigue properties of these materials and really connect them over to the tensile properties. So in a way that it allows them to explore a more narrow collection of material processing parameters. We also, play games with trying to discover different yield surfaces, looking at tensile compressive asymmetry, and really developing frameworks so that materials that are anisotropic can be characterized in an efficient way. And so this is some of the work that was done by a former student as well. Okay, so I think I'm closing in on the end of my time here. So I'd really like to thank the former students that are in my group. So I've got a number of students here who are off doing successful things. I have a student who's Calvin. He's at the University of Texas El Paso. Scott, he's a student. He's a director of engineering at Doosan, and all of my students are out there doing really great things. And I think without them, they are our work really doesn't get done at the same level. So I still have a lot of good students that are in our group, and I have great things coming from them as well. So I think with that, I'd also like to thank our collaborators and our sponsors for supporting our research. And I think I'm at the end of my time, so why don't we maybe close there.